Okay, so here's another influence line problem we're going to do. This time we're going to construct the influence line for the shear at C. Okay, so what do we want to do? I need to find the shear at C, right? Well, if I cut the structure here to find the shear at C, I can either work the left side or the right side. I'm just going to decide to work the left side. So if I do that, I'm going to need to have my reaction. So first thing we'll do is I'll come in and say, well, here's my reaction, AY, and I'll have one over here at BY also. So this problem is going to require me to first find the influence line for the reaction at A. Just like the previous problem, I'll go ahead and indicate my unit load and also tell you that it's operating at some distance x from A. So first, let's find our AY for this. So I'll come over here and we will sum moments where? At B. Set those equal to 0. So what type of moment, or what is the moment of the unit load about B? Well, it's positive. And what is the moment arm? It would be this distance, which is 12 minus x. Everybody see that? And then, of course, I would have a negative moment created by AY with a moment arm of 12. So I can solve for AY. What is AY equal to? It looks like it's equal to 1 minus x over 12. So, when x is 0, which means my unit load is right above A, AY is 1. And then it decreases linearly all the way to where I get to B. When x is 12, AY goes to 0. Alright, so now I'm ready to draw a free body diagram of the section to C. So what is AY? What is my reaction AY? Oops, sorry. Keep moving my paper. Well, we just solved for it, right? It's 1 minus x over 12. This distance is 3 feet. And then we're going to look for, we're doing shear, right? Yeah, so I'll do, there's my positive shear at C. Now the first case we'll do is where the unit load, 1, at some position x, is on the structure. So this is equivalent to x being between 0 and 3. Okay, before we solve the problem, I'll go ahead and redraw the same free body diagram with the same reaction, 1 minus x over 12. I'll assume the same behavior for the shear at C, except what's happened? My unit load has moved past 3 and is no longer on the structure. So this will be valid from 3 to 12. Everybody see the difference? So all I have to do now is just apply with the things we've done previously and solve for the shear here. And when I do that, I'll have the value for 0 to 3. And then I'll solve for the shear with this free body diagram, and I'll have the distance, or the value from 3 to 12. So let's start with the first one. To find shear, I'm going to just sum forces in the y direction. I'll assume up is positive. So I have this force acting up. So there's my 1 minus x over 12. That's acting up. There's my minus 1 down. And then there's my shear at C down. So what is the shear at C? Well, it looks like the 1's cancel. right? It looks like I'm just negative x over 12. You see that? Let's do the same thing here. We'll sum the forces in the y direction. So I have AY acting up, 1 minus x over 12. Now my one force is left, so I don't have to worry about that. And then I just have minus my shear. So it looks like my shear force is just equal to 1 minus x over 12.
So you don't have to go to the other side, you stay on the same side.
If I did go to the other side for the range 3 to 12, then the unit load would be there.
Okay.
If I use the right-hand free body for 0 to 3, it would not be there. So what I suggest to you to try to keep things straight is pick a free body, and you'll have one case where the load is on that free body, and you'll always have a second case where the load is no longer on that free body. So now I can plot this. So again, we're plotting the shear at C as a function of x, where x is the position of the unit load. Oops. And I'll go ahead and mark off 12 and 3. So from 0 to 3, I use this equation, which is, starts off at 0, I have a 0 value, right? And then at 3, I have what? Negative 0.25. So it looks something like this. Yeah.
I'm turning a calculator.
Oh, okay.
Sorry.
So this would be negative 1/4. And that's over 3 feet. So what happens from 3 to 12? Well, if I put in 3 here, what do I get? I get 1 minus 3/4, and that gives me 3/4. And then it decreases to 0. And you end up with the graph that looks something like that. And this value here would be 3/4.
So the value right there at 3 on the negative side of that graph, what was that again?
This value is negative 1/4. So what happens is the shear at C, so as you approach C from the left-hand side, the shear increases linearly, maxes out at negative 1/4. As you pass C and go to the right-hand side, it shoots up to positive 3/4. And then as you move to the right, the shear at C decreases to 0. Now there's one thing to notice while we're here is this change here. So the change in shear as you pass the point is always equal to the load. That is something that we did kind of see when we talked about shear and moment diagrams. Remember that? That's a characteristic that we're going to take advantage of in the future. We'll always know that as you move from the left-hand side to the right-hand side, that the change in shear is equal to our applied force 1. So where would you go stand or ride your unicycle to create the maximum positive shear at C?
Just past C.
Just to the right of C, and you would be 3/4. So if you weighed 100 pounds, that'd be 75 pounds of positive shear. If you back up 1 nanometer to the left, the shear suddenly is only 25% of that, or 25 pounds, and it's negative. So you can imagine if you are a shear connection at C, and lots of loads are passing over you from left to right, you're constantly changing direction, positive, negative, and at different magnitudes. So you have quite a busy existence as a shear connection.
That's the maximum shear the beam is at 3?
That's for that one load.
For that one load?
For that one load. Now, of course, remember, we're using superposition, so if the load changes from 100 pounds to 1,000 pounds, it just scales up. And today is Thursday. On Tuesday, we'll talk about what happens if you have multiple concentrated loads, moving together like, for example, representing the axles of a truck or something like that. Okay. Any more questions before I stop it? All right.